Welcome to another video. This is the second part of the dynamic power topic that I started last time. So if you haven't watched previous video, I think it makes sense to watch that before this one so that you get an idea of what I'm trying to do. In this video, I'm going to explain how I came up with these two, or how you can generally come up with these two and not. You find those in pretty much every book, but sometimes there's a little trouble in understanding it. So I thought, okay, it'd be nice if I do another video where I can explain how we reach to these two formulas. Okay, so in the last video I just showed this one, that okay, is just energy taken from the supply in in a transition which involves going 0 to 1 and 1 to 0. Is this, and then during when PMOS conducts, you are charging this capacitor. So then in when the PMOS is on, you the energy sorry, not this one, this one's, I'm really sorry. So this is the energy supplied by the supply voltage, which is connected here when PMOS is on, because this circuit is on. This is how much the energy is stored on that capacitor. And so it's CLVDD square. This is how much stored. So you must be wondering, where is the remaining one? Remaining one is actually dissipated. Is spent in fighting against this resistance. That you can say that. And when NMOS is on, this energy that was stored on this capacitor, this actually goes to ground through this. So how did I come up with this and this? Once you these two, not this is simple. Okay, so all right, not this one. This is I already covered. Okay, this one. So first phase, when PMOS is on, input is 0. You can think of transition 1 to 0 happen on the input. Input is 0, so PMOS is on. Current flows through this, and this current it goes through a change. It starts charging it, so then its charge goes slow down. So while think of that VDD is this is VDD, so this doesn't change. This was already VDD. Okay, it's not like we are changing this from 0 to VDD. This is fixed at VDD. It's the current that actually changes as we turn the PMOS on, and eventually in steady state, it becomes in steady state. Actually, it changes. So the point that I want to mention, sorry for going back and forth, point that I want to make is the current is time dependent here. That's it. And your output voltage here it also changes from 0 to VDD, or it goes all the way to VDD. So let's look into the equation for energy. Energy, as I mentioned, is instantaneous power, and then you multiply with the time over which you are calculating that energy. Okay, so power into time. In case you're wondering this equation, if you this is this power is energy over time. So if you want to calculate energy, you multiply that with time. So power into, again, you're looking into very small change here. I mean, that's you add each small change, we calculate what is the instantaneous power. They multiply these two, and that gives you energy. And that curve from 0 to the time period that we're interested in, we just integrate it over that time. That's really the main thing that you need to understand. The rest is solving this integration. So then you replace some of the things. Okay, power is what? Is voltage, time, current. Voltage is fixed at VDD. Current is a variable which varies with time. Then you bring VDD as is. Current in a capacitor, if you remember from my previous videos when I talked about capacitance, is the capacitance that is connected there multiplied by rate of change of output. That's a typical formula. It's a very basic one. Even in high school, you must have learned that. So that's the current through a capacitor formula. Always we kept VDD dt. This is a constant. This is a constant. Just assume that as most majority of this capacitance remains the same. Some components of this capacitance, especially which are connected to gate, they can change, but in the steady state, let's assume this is constant. Bring this integration into this change, and this whole thing is really the total change. The change of voltage with respect to time, the total change in one cycle is what really the maximum change can happen is can go from 0 to VDD. So the total change is VDD, which is equal to the supply voltage. You cannot go beyond that. So put that VDD, CL, and this replaced with VDD. So we came up with CL VDD squared. That's energy supplied from here. Now, how much energy is stored on the capacitor? That's another interesting bit. And that is on this side. Sorry, I cramped a lot of stuff in a single page. I just want to make sure you have things in front of each other. So here, we have a little bit different start. So think of that, the charge on a capacitor, the basic formula from high school that you might have remember is Q CV. C is the capacitance, V is the voltage. We are interested in a small change, that tiny change that happens. Again, we will integrate it over the required voltage. So just put a D, remember that delta, Q, C, delta, or small change in V. To charge capacitor from 0 to VDD, we need to get some work done. Okay, and the work done is W into voltage into charge. Okay, how much voltage applied to carry out how much charge, something like that. Think of it. It's a small change, so put D here. Now the energy is the actual amount of work done. If you remember the formula I put here, amount of work done, or let's say during a single event. So amount of work done during a single event, and the amount of work done, formula for that is voltage into charge. So it's, if you think about, okay, small work done, and if you say from when voltage changes from 0 to VDD, important thing here is in this side your variable is voltage, and this side your variable was time. Understand? So here I'm putting, if you look at W, the actual small work integrated from 0 to VDD, that work is multiplication of V out into delta charge. This is the instantaneous voltage at a particular time, and this is a small amount of charge. Then what we do is charge is back to this equation, C dV out, change in voltage. Bring this C, which is actually our CL out, V out, this is changing voltage. and we multiply it with the instant voltage with the amount of change, and we integrate from 0 to VDD. I'm not teaching integration. I have forgotten that too, to be honest. But if you integrate this one, you come up with VDD square over 2, this thing. And then half CL VDD square, just rearrange that. All right, so what is the note here? I forgot that. So this voltage at the output, not with respect to time, but there's, oh, I'm sorry. With respect to, since we have a changing voltage, so it's important. I think that's why I mentioned that, because I was confused myself. And here you have current with respect to time, and we're integrating 0 to t. And here V out is changing with respect to voltage, not with respect to time. So dV out is changed with respect to voltage. All right, sorry if I confused you. And these were exactly the things that confused me when I derived this, and I was looking at few books, and I thought, okay, what's happening there? So that's the key thing, if you remember. So sorry, since I forgot an integration, I didn't explain that one. So dV out means it's change with respect to voltage. So voltage change from 0 to VDD. So I really hope that I have done some decent job in explaining you this. And these concepts, again, if you remember this one, you don't need to look into how we came up with this one, but sometimes you are curious, okay, how did you come up with this one? Because this is the equation we are really using to optimize power. But you need to have, people will not ask you again and again, but at least you need to have idea, oh yeah, this is how it came up with this. And half CL VDD square was also important, because I said it's only half CL VDD square stored, not a full CL VDD square. I mean, it makes sense, because when charging this, there is a resistance on this path. So there will be some dissipation. But how much it is? So mathematics tells us that is half and half. And this half doesn't depend on the transistor size and all that. It has to dissipate that. So if you reduce, the only way to reduce that dissipation in PMOS is to reduce this load, you reduce this voltage. All right, I think that's it. This is where I just summarized exactly the same thing that I mentioned. So this is a short video. In the next video, we will look into the other components of power. The first we'll look into the short circuit power, and the second one will be the leakage power. See you then. Thanks. Take care.